Well, I think we might kick off this final session of PyCon 2017. Our presenters today are from Yelp. They are Amit Ramesh and Qui Nguyen, and they'll be telling us about building stream processing applications. Please make them welcome.
Hello, everyone. Welcome to our talk. I'm Amit.
I'm Wee.
And we're engineers at Yelp who work on the ads platform. And here we are talking about stream processing, and more specifically about building your own applications using stream processing. So depending on where you are from, you may or may not be familiar with Yelp. Yelp's mission is to connect people with great local businesses, and via the website and the mobile apps, we build the tools that make this possible. And with that, I'll turn off my PR mode and go back to my engineering mode. So here's what we plan to cover during this presentation. So we'll start off with some motivation for stream processing, and then we will come up with an example problem that we want to solve and walk through the solution. And then we'll cover some more general principles that's going to be useful when you build your own applications. So why stream processing? Well, clearly there's data coming all the time, hitting us, bombarding us, whether we like it or not. And it could be in various forms. It's continuously coming in. Maybe it's a measurement of a sensor, something like a Fitbit device producing these measurements. Or maybe it's just like people clicking on ads, generating events. And you probably want to make some kind of meaningful, you want to extract something meaningful out of these. Maybe the average value over the last minute for the measurements makes sense in order to take a decision, or maybe total clicks for ads on a day makes sense to find out how much your campaign is doing, how well your campaign is doing. So traditionally, all the data has been coming in continuously. Invariably, they ended up in files, log files more specifically, and which meant like the most natural way to handle the data was batch processing, wherein it's kind of like a food processor at home. I mean, you have finite amount of data that you want to process. You just push it through the processing pipeline all in one go, and then you get the results at the other end. But more recently, frameworks such as Kafka are enabling more streaming kind of semantics, and so there is definitely a shift towards, mainstream shift towards actually doing stream processing. And so in contrast to a batch process, a stream processing situation would be where you have data coming in all the time, and you're continuously processing that data. Now, why stream processing or batch processing? Well, clearly, you're reacting faster, which means you're getting your results faster. But there's also some quirks with batch processing that actually don't quite exist when you start doing stream processing directly. So to give you an example, let's say you have data for day 12 and day 13, and you're doing some kind of operation on a day-to-day basis. Maybe you're processing in the West Coast, but maybe the results are meant for the East Coast. And so clearly, there's this day boundary that doesn't quite match up on the two ends. So things like that, you'll have to basically work on, kind of resolve, and especially if you want to support both the East and West Coast and such. With stream processing, things are a little more naturally set, where you can have a window, and that kind of moves or slides over, and that way, things are more naturally solved within a stream processing context. So at Yelp, and specifically in the ads team, our own evolution has kind of been similar. Like over many years, we've been doing batch processing of events, of log files. And then more recently, we've been investing time and resources towards stream processing. So to set some context, let's say there is a business that has a presence on Yelp, and now is trying to advertise so that they get more aware, users are more aware of that. So if a user using an app, let's say it searches for Thai food, what might end up happening are a few ads may be shown above the search results pertaining to the business that wanted to advertise. So now the user may choose to click on the ad, or maybe they call the business. So these are some events which can be tracked over time and aggregated. And we eventually produce reports for the advertisers so that they get to know what kind of impact their advertising has made out there. And the way we've been traditionally doing it is through nightly jobs. So essentially, we go over the logs, we have Hadoop jobs running overnight, and they're producing these, or crunching through and producing the reports so that we can share it with the advertisers on a daily basis. But in the last couple of years, we also introduced like a phone app for business users, where they can actually see how their campaigns are doing. They get their metrics on their phones, which means it naturally makes sense for us to present this data on a more granular level, like as in not at a daily or a nightly basis, but like a more continuous basis. And so we're kind of headed in that direction where we're working on internally having more systems work in the stream processing realm, and then eventually surface it at some point to the external world as well.
All right, so now that we know what stream processing is, the next section is going to be about putting one together. And the rest of this section is going to be in the context of an example problem similar to something that we're working on at Yelp, but a little bit simplified. And that problem is going to be ad campaign metrics. So the metrics are going to be numbers like the number of views and clicks that our campaigns are getting. And a campaign is just a package that a business owner buys from us. So basically, we want to get these metrics per business. So you can imagine we have events associated with ads in many different parts of our system. For example, we might have one log where we log when the ad is actually served from our back end, another one when the user views the ad, and another one when they click on it. So they might look something like this, where the ad log has the most information about the advertisement itself, and then the view and click logs just say what ad they're associated with and the time they occurred. And what we want to do is combine all these events together from the different parts of our system and get these metrics over time.
But before we actually try solving this problem, let's figure out what are the tools available, what's the arsenal that we have to build such a system. So first off, at a very high level, a stream processing pipeline looks something like this. I mean, you have a source at the one end, a streaming source, and then you have a stream processing engine, which is where you will have most of your business logic, and then the data sink, where it could be another streaming source if you want to chain stream processing pipelines together, or it could be maybe a traditional database so that it can downstream systems can just query on off of them. And in our case specifically, we use Kafka for the streaming source. We use Spark Streaming for the actual processing, and use both Kafka and Cassandra depending on the use case for the data sink. So in terms of the processing side of things itself, I mean, like, so there are these basic categories of operations that you can do, and we will go through each of these in a little bit of detail now. So first of all, ingestion. Like, clearly, you want something that pulls data from your streaming source into your pipeline for processing, and that's, of course, going to be your first stage of your pipeline. So if you, for example, consider Kafka as your source, then you would need something which is Kafka-specific in terms of like talking the right protocol, in terms of talking the right semantics, and translating the data from Kafka into the pipeline. And so as an example, so this is a Spark Streaming example where you import a specific utility which is Kafka-specific, and then you create your stream, and you provide the Kafka parameters it needs so that it can talk to Kafka and create a stream that's then handed down to the operation that's coming next. So once you have the data, the simplest thing you can do are stateless transforms, wherein you're really focusing on a single event at a time. So all you're doing is within the context of a single event. So an example could be like a filtering operation. So you have data coming in, events coming in, and maybe you have some criteria based on which you either drop events or let them pass through. So an example could be, yeah, you have these ad events coming in, and maybe some of these IPs are from bots. And if you have some kind of a blacklist, then you can use that to just filter out the ones that are from bots and only keep the ones that are genuine. Another example of stateless transforms could be projection, where your events may have fields that you don't really care about, and so you're just trimming them down and only keeping the fields that you really care about. So again, an example could be like, yeah, you have ad IDs and campaign IDs, which you care about maybe for subsequent processing, and so you just keep those fields and their values, while dropping all the other keys away. And then the next level of interesting is stateful transforms, where you're now concerned with not just a single event at a time, but actually a window of events at a time. And you could basically do like sliding windows where you have overlaps, or you could do tumbling windows. I mean, most frameworks support like multiple kinds of windowing operations. But the central idea is that you're going to apply operations over multiple events. And let's take an example, actually, to make it more explicit why we call these stateful transforms. So let's say this, we're trying to aggregate numbers, just simple numbers, where each event contains a single number. We're summing them up based on the window and producing the results. In this case, now in theory, you're basically going to go through every event, or you're going to get one event at a time, which means that you have to keep the intermediate results of the summing that you're doing before you can get to the end of the window and then emit that sum. So there is a state, there's this intermediate count or the accumulation that you're doing, and that's kind of, that's the reason why it's a stateful transform. And of course, you can imagine that, well, this was a very simple case where you had a single number to hold on to, but depending on what kind of operation you're doing, it may be a more complex state. And here again, the example here, it's a pretty straightforward API in Spark. And so you just do a reduce by window. You provide the standard Python add operator there, and then you can specify the kind of windowing you want to do, and then you have the results on the other end. And then the next step would be doing something like a keyed stateful transform. So here, we are still applying operations within the scope of windows, but then we're also trying to group by keys. So colors are used here to kind of distinguish keys. So you have the orange and the green. And what you see here are there's a bucketing by color or by key. And there's an implicit stage in these cases called shuffle, which is where the shuffling or the grouping of keys takes place. And then subsequently, you apply whatever operation or transform you want to apply on the data that's been collected or grouped together, which is represented by darker shades of color here, just to say, OK, there's some processed version of that data. So an example for this would be, let's say you have the ad events we were talking about earlier, and people viewing these ads. And so you have color-coded campaign IDs right now. So you have two campaigns, green and orange, or 1 and 2. And here again, you have a field called views, which is just count of number of views. And then on the other end, you have the things summed up by the corresponding keys. And again, the code is pretty straightforward because there's a direct API again, where you just say reduce by key and window, and then you just have the same operator and whatever windowing you want to choose. And there's another way, or there's something else you can do also with, in the case of keyed stateful transforms, where you're not just dealing with a single stream, but actually dealing with more than one stream. So it's more like a join operation in this case. And here again, it's pretty similar in the sense that you still have the shuffle and things going on, grouping by key, except that your original source had 2 streams. And then the final join is some kind of a combination of the records that were brought together. So here's an example where you have 2 different streams. One is the ad stream, and one is the view stream. And we want a consolidated view of the entire thing that's happening. And so we bring those corresponding records together into a single record, and that's basically your output. So that's an example of how you do this. And in terms of code, again, it's pretty straightforward. You essentially just apply windows or define windows for the 2 streams that you have. And then when you actually apply a join, the join is always in the context of the windows that you were defining earlier. And finally, you have the publishing phase, which is kind of the other end of the pipeline, where you have to write to some kind of sink. And here again, it has to be specific to the sink that you're writing to. A simple example could just be like, yeah, maybe you're saving it as text files on S3, and there's a direct interface for that. So in summary, we need ingestion to get the data into the pipeline. We can use stateless transforms whenever we're just acting on single events. Stateful transforms if we're actually acting on windows of events. And keyed stateful transforms if you're not only operating on windows, but also like wanting to group by a certain attribute or key. And finally, publishing to actually make your results available to external systems.
Okay, so we have all the pieces now. So let's go back to our example and put them together to get the campaign metrics. So remember, we have the ad, view, and click logs, or event streams coming in. So the first stage is reading them. So we have a couple events in our ad stream. We filter out the ones that maybe come from spammy IPs, and then trim down the fields. So here's a scoring field in the ad log that says how this ad was chosen. We don't need that for our final campaign metrics, so we'll take that out. And you can imagine that the view and click logs go through similar stages where we trim them down to exactly what we want, so that we don't have to send as much data around when we get to the joining stage. So in the joining stage, we want all the data for a single ad together. So here we have the same ad, the ad and view data for it. So the join puts them together in a single event. And then we can further do a transformation, pulling out the data we want, the campaign ID, whether or not there was a view. Finally, we put together events from different ads, but the same campaign, add together the number of views. So here we have 2 views and 1 click. And that's the information that we wanted, so we can write that out to the database. So here's a full picture again. Hopefully that gives you an idea of how you can put these operations together.
So now that we spoke about a specific example, some operations that you can do, and very specific solution to a problem, let's kind of step back and talk about some more general principles that are applicable to design of stream processing applications. So the first one we'll talk about is horizontal scalability. So let's say you build an application, you have a solution out there, and maybe looks like this. You have some data, you have some processing going on, and it's working fine for a while. And then maybe someday you get hit by a load of data, and then it just squashes your application. And that's basically not the kind of design you want. So the central idea of horizontal scalability is to kind of design your solution in such a way that the data can always be broken down into reasonable chunks and be distributed across your processing resources. And the only thing you will have to do is probably throw in more machines or throw in more resources to solve the problem, but the design should kind of stay unaffected by it. And why would you care about this? Well, for the most part, I mean, there's always growth in data that's expected. Like if you have a website or whatever other source of data, it's very likely that data will grow over time. And so it's good to have a design that's able to scale very easily with the growing data. Or even if you don't have such a situation, you could always end up with a situation where you have some kind of differences in terms of how much data you get maybe during different times of the day, maybe on a weekly basis. And so if there's like a radical difference between the peaks and the troughs, then again, it makes sense to have a design that's horizontally scalable, so you can actually save some cost by like having fewer machines, say, during the troughs, and then adding the machines when there are peaks. And there are also like automated solutions for this, like auto-scaling solutions where you can essentially have this automated. All right, so how do we go about actually doing it for a stream processing application? Well, it turns out it's pretty straightforward because the events are already discrete enough that they're just coming in sizable chunks that can be handled. And all you need to do is just divvy up into multiple partitions. And so you can just parallelize it as much as you like, depending on the resources you have. And that way, you're just going to spread this data. And going back to our example from earlier, like clearly the first 3 stages where they're all like stateless transforms, this is like readily applicable because each one is just working on a single event. And so it really doesn't matter where that event ends up. And so they can basically distribute the work across themselves. And you can pretty much scale that way. But if you look at the second stage in that processing pipeline, where we're joining by add ID, now clearly you don't get to just randomly throw things around. So this would be the case where you use keyed partitioning because you're actually using the key to determine the buckets or how you want to distribute your data. But it still is something that's pretty straightforward. All you have to do is just use some kind of hashing to the bucket things. The one thing to watch out for, especially with keyed partitioning, is the possibility of hotspots or data skew. So what do I mean by that? Well, let's take the next stage in the pipeline where we were trying to sum by campaign. Now, it's quite possible that you have some two different ad campaigns which behave very, very differently. So for example, maybe there's a restaurant that's advertising, and then there's probably a bike shop that's advertising. And clearly, the restaurant one possibly can reach most people, while the bike shop one is probably a more narrow, restricted subset that it wants to target. So the data might end up looking like this. So the red one's representing the restaurant, where like just too many ads, and then you have the blue one, which is the bike shop, which just has a few. So it's quite possible. So this is like a situation that can pretty much occur for any kind of problem. And there are mitigation solutions, mitigation strategies to kind of overcome this kind of skew and resolve it in a way that things are balanced. But we don't have the time, and so it's out of the scope for this particular talk. But I do encourage you to look it up online or talk to us after, and we can go over that. So in summary, use random partitioning. Whenever you have stateless transforms, you can use keyed partitioning for keyed transforms. And definitely watch out for hotspots and use mitigation strategies to eradicate those.
Okay, the next two principles that we're going to talk about are related to handling failures. So once you've distributed out the work in your application, any of the machines that you're doing work on could fail. So idempotency and the trade-off between consistency and availability are things that you need to think about. So idempotency, just in case we're going to review, an idempotent operation is one that can be applied more than once and have the same effect. So we want this because if any operation in our pipeline fails, for example, the projection or the write, we want to be able to retry that. And idempotency allows you to reason really easily about what the effect of that retry will be without worrying about its effects. So transforms like filters or projections where you're not updating any state are idempotent, whereas stateful operations like things with local state or where you're writing out to a data sink, you need to think more carefully about. So here, it's that write stage that we need to design for. And some writes can be idempotent. For example, if you're writing to a unique key, one campaign, 1 minute, we're saying that there are 2 views there. Obviously, no matter how many times you write there are 2 views, it'll still be 2, so that's idempotent. In contrast, if you're doing something like an increment where you're saying you want to add to the number of views, of course, if you do that more than once, the result is different. So increments are a pretty common operation, so some databases do try to add support for idempotency. There are a lot of different solutions, but one of them is adding some kind of version to the operation. So you're saying, I'm updating this specific version. And then if the database is keeping track of those versions, then it'll know that it's seen an update for that version before. So this becomes idempotent because no matter how many times you send that update, the database will only apply it once. So back to streaming pipelines in general, we just talked about an example related to the data sync, but it's also important in the local state when you're doing something like a stateful transform, like joining or some operation over the window. Because any event could be reprocessed, and that'll affect the local state that you're maintaining. Some frameworks try to provide exactly once guarantees on the reprocessing, but what they're doing under the hood is analogous to what the database is doing. They're adding extra information so they can keep track of what they've already processed. So it's important to understand the mechanism that they're using to guarantee that. Okay, and then the final concept we're going to talk about is consistency versus availability. So basically, there's always a trade-off between these two things when you're handling failures. Consistency, we're going to say, is every read seeing a current view of the data, and then availability is your system's capacity to serve requests. And this is a fundamental trade-off when you're doing distributed systems and trying to handle failures between them. So to see why, we're just going to do a quick example with a replicated data store where 2 machines are trying to keep track of the same state. In the happy case, when someone updates the value of A, one machine will tell the other machine and they still all agree. But in the situation where they're not able to communicate with each other, then we need to make this trade-off. For example, if someone tries to write A = 3 and that machine isn't able to communicate to the other one, then a consistent solution would be to reject that write, but that makes writes less available. And if we wanted to accept that write, then during the time when the machines are unable to communicate with each other, then you have this inconsistency where one machine doesn't see the most current view. So again, this is pretty fundamental to all distributed systems, so it's important to think about in your data source and data sink. Some systems make a specific choice along the spectrum, so you should be aware of what they're choosing and make sure it fits your application. Others do let you be more flexible. For example, Cassandra allows you to choose how many replicas have to respond to a write before it's successful. So the more replicas that need to respond, the more consistency, the less availability. And one thing to keep in mind is streaming applications are designed to run continuously. So usually you want to prioritize availability because you don't want your application to shut down in case your sink or source become slightly unavailable. But in some cases, for example, if you're using the data in your application, our views and clicks for billing advertisers, in that case, we might actually care that the data is the most current and accurate. So if you want to prioritize consistency, then you need to add some extra retries to your application to make sure that you can handle unavailability sometimes. Right, and then in other cases where it's less critical, then you can prioritize availability. All right, so that is the end of our talk. Basically, stream processing is just processing on events as they come in. You can have operations on single events or over windows of events. Something to keep in mind is trying to keep your design horizontally scalable because data often grows and changes over time. So you want to make sure that your partitions are even as possible. And then because streaming processing any event could cause a failure in your system. Handling failures appropriately is really important. You want to try to keep your operations idempotent and make sure you're making the right trade-off between availability and consistency. Right, so we hope that we've given you a good foundation for trying to build your own application. And before we end, we do want to say that we are hiring at Yelp across the board, including for data processing. And if you're interested in reading about the work that we do, check out our engineering blog, and we also have a lot of open source libraries related to Python on our GitHub. Thank you.
So if you have any questions for Amit and there is a microphone here in this aisle. We'll just see if anybody wants to line up. That looks like a yes. Go ahead.
I will try to make this quick. At my organization, we haven't gone from a batch style processing because of possibility, or actually the recurrence of delayed messages coming in and what that does for consistency. And much of our data coming in is used for billing. Is there a way of gradually going to a streaming approach but dealing with potentially 12-hour delayed messages that you need to retry or something to that effect? Like how can you still do a streaming approach but deal with this eventual consistency of nodes that might be offline for 12 hours?
Sure.
Go ahead.
So definitely many of the stream processing frameworks that exist today are moving in a direction where they do support like delays. And what it typically means is that you have to basically provide it with more resources. I mean, clearly, if you want like a 12-hour delay, then you want to have enough memory or buffer or whatever backup to actually support that much state. So it's basically a stateful operation at that point. And so it really comes down to the resource you throw in. But definitely, frameworks are beginning to abstract out things enough that you can just say, OK, this is my delay, or this is how much delay I'm going to tolerate, and work towards it. I mean, it's still kind of early on in the sense that they're not at the stage where they're like robustly handling this, but definitely things are moving in the direction where you have less to worry about, and the frameworks actually take care of it.
Okay, that's all the time we have. Everybody, please thank Qui and Amit for a wonderful talk.
Thank you.
Now, there's a keynote downstairs starting in about 10 minutes' time in Expo Hall C. So go and get to that, and PyCon will wrap up at that point. So thank you all for being a great audience, and see you next year.